Let's look at question number 14, part A of the pure maths paper. So this is the differentiation and graphing question. So they have given fx as 2x plus 3 over x plus 2 squared, where x is not equal to minus 2. Show that f dash x, the derivative of fx, is given by that. So let's first find the derivative. So this is just a simple application of quotient rule, right? So f dash x, so apply the quotient rule. X plus 2 squared, whole thing squared. Right. Then x plus 2 squared here times the derivative of the numerator, which is 2, minus 2x plus 3 derivative of the denominator, which is going to be what? 2 into x plus 2 times 1, using the chain rule, right? So now let's simplify and get that. So take x plus 2 out, no? 2 and x plus 2 both we can take out. That is common from the numerator. So you are left with x plus 2 from the first term, and in the second term you are left with minus 2x plus 3 equal, sorry, divided by x plus 2 raised to 4th power. Now just simplify. 1x plus 2 I can cancel, and I have 2 outside. X plus 2 minus 2x minus 3 x plus 2 cube. Then we have 2 minus x minus 1 over x plus 2 cube. So now just take the minus sign out from the bracket in the numerator. So minus 2 is minus 2 into x plus 1 over x plus 2 cube, right? So there's the derivative. So first part is done. Derivative is minus 2 into x plus 1 divided by x plus 2 cube. So this is just simple application of quotient rule, right? Hence find the interval on which fx is increasing and the intervals on which fx is decreasing, right? So then we have to first do what? Find the stationary points. No? What are the stationary points? Stationary point, we can do f dash x equals 0. So that gives you better to do the critical numbers. No, we will find the critical values rather than stationary points. So if dash x equals 0, you get minus x minus 2 into x plus 1 equals 0. So x equals minus 1. And f dash x does not exist when the denominator is 0. No? So x plus 2 equals 0. X is equal to minus 2, right? So now we can find increasing decreasing intervals. I can break the number line into 3 sections, no? Minus 2, minus 1. So before minus 2, between minus 2, minus 1, and after minus 1. So we need to check the derivative sign. No? If the derivative is positive, it is increasing in that interval. If the derivative is negative, it is decreasing in that interval. So for the first interval, let me use test value. Easy test value use. Anything less than minus 2, I will use minus 10. So I have to substitute minus 10 into the derivative. What do you get? What's the derivative sign? substitute minus 10 here, so you get minus 2 into minus 9, which is plus, no, plus in the denominator, and minus cube will become minus, no, so plus over minus is what? Total is minus. So derivative sign in the first interval is minus, so this is decreasing. So when the x values are less than minus 2, the function is decreasing. Now let's check between minus 2 and minus 1. So let me use minus 1.5 as my test value and substitute up here to the derivative. So minus into minus again, so again the numerator is plus, then what happens? Minus 1.5 plus 1 is minus 0.5, so yes, plus, then minus 1.5 plus 2 is 0.5, no, so the denominator is also plus, so the total is plus, so the final sign is plus for the derivative in the middle interval. So this is increasing between minus 2 and minus 1. Now let's figure out the final interval greater than minus 1. So what's the easiest test value? 0. So the numerator becomes minus 2 into 1 is minus, no? Denominator is plus, so the total sign is minus. So this is decreasing when it comes to values greater than minus 1, right? So then let me write increasing intervals are what? Increasing is between minus 2 and minus 1, increasing interval. It is decreasing for what? Maybe let me write it in interval notation better. Minus 2 to minus 1, increasing, decreasing minus infinity to minus 2 and minus 1 to infinity. So it is increasing, sorry, it is decreasing in those two intervals and increasing between minus 2 and minus 1, right? Right, so that is done. And they also want us to find the coordinates of the turning point. So turning point happens at the stationary point, no? So we found x equals minus 1. So what is the y value? Substitute to the function. Okay, substitute to the function to find the turning point y coordinate. So fx equals was what? Fx equals 2x plus 3. So I have to substitute x equals minus 1. So over x plus 2 squared over x plus 2 squared. So minus 1 plus 2 squared. So we have 1 in top. Yes. So 1, y equals 1. So the turning point is minus 1 comma 1. Right. So let's look figure out whether the turning point is a maximum or minimum also, because when we want to draw it, it's better to know that. Yeah. So we can use our f dash sign graph to do this. So increasing before minus 1, that is this shape, no? Then decreasing after minus 1. So that is which shape? This is a local maximum, no, this is max shape, no? So local maximum at -1 comma 1. So keep that in mind also. This is a local maximum, a peak, right? Okay, then what is given? It is given that the second derivative is given. Find the coordinates of the point of inflection of the graph, right? So second derivative is given. Second derivative is what? 2 into 2x plus 1 x plus 2 raised to 4. Again, x is not equal to -2. Find the coordinates of the point of inflection of the graph. So then I have to find what? Critical numbers of the second derivative. So f dash equals 0. That gives me what? 2x plus 1 equals 0. The numerator has to be equal to 0. X equals minus half. And if double dash does not exist, when x plus 2 equals 0, so x equals -2, right? So let me do a sign chart for the second derivative now to figure out the inflection points. So -2 minus half, right? And this sign chart will be important for the graphing part also. F double dash sign. So we'll use what are the test values? Mine less than -2, no? So I will just use -10. So this one, the denominator, look, the second derivative denominator is always positive, no? Why? It's a fourth power. It doesn't matter which value we put for x, it's always positive. So the sign depends on the second derivative sign, only depends on the numerator. So when I substitute -10, numerator becomes minus, no? So this is minus, so that means concaving down. Concaving down before -2. Between -2 and minus half, I will substitute -1 as my test value. What happens? Minus, again minus, no? So second derivative sign is minus, so this is also concaving down. After minus half, what happens? Test value I can put 0, so positive. Positive means concaving up. So -2 is not a inflection point. It can't be also, no, it is not in the domain, no? Minus half is an inflection point because why? Concavity changes from down to up. So this is your inflection point. So our inflection point is x equals minus half. What is the y value? Substitute to the function. So 2 into minus half plus 3, 2x plus 3 over x plus 2 squared. So minus half plus 2 squared. So what do you get? -1 plus 3, 2, 1.5. So 1.5 is 3 over 2. So 3 over 2 squared is 9 over 4. So 8 over 9 is the y value. So then what is our inflection point? Inflection point is minus half comma 8 over 9, right? So inflection point is also done, right? Find the coordinates of the inflection point. So that is done, right? Now sketch the graph of y equals fx indicating asymptotes, turning point, point of inflection, right? Point of inflection found, turning point found. We need to figure out the asymptotes, right? So let's now find the asymptotes before drawing. For the asymptotes, we have to use the function. Fx is what? 2x plus 3 x plus 2 squared. So you get the horizontal asymptotes when the denominator becomes 0, right? For the values where the denominator, wait, not horizontal, sorry. You get the vertical asymptotes just what? Equal the denominator to 0. This is the shortcut way that gives you what? You have a vertical asymptote at x equals minus 2. So these are how do you actual definition is what? You can do what? When x goes to 2 plus, what happens to fx? Check that. When x goes to 2 plus, sorry, not 2 plus, minus 2. When x goes to minus 2 plus or minus 2 minus, what happens to fx? Fx will go to infinity, no? Minus 2 plus, wait, let me check what will happen. Minus 2 minus, oh no, it will go to minus infinity, no? So then you have a vertical asymptote, no, at x equals minus 2. When x goes to minus 2 plus, your fx function value goes to negative infinity. So you have a vertical asymptote there. For the horizontal asymptotes, what happens? What happens when fx goes when x goes to infinity? When x goes to infinity, what happens to this limit? When x goes to infinity, fx goes to 0, no? So your horizontal asymptote is what? Y equals 0. When x goes to infinity or negative infinity, yeah, you get fx equals 0. So that is y equals 0. So horizontal asymptote is y equals 0. Vertical asymptote is x equals minus 2. Right. Okay. Right. Now, using all the things we found, we can draw the graph. So when you are drawing this type of graph, first mark the asymptotes. So I have a vertical asymptote at x equals minus 2. So with the dotted line, I will mark that. So there's the vertical asymptote, x equals minus 2. Then there's a horizontal asymptote, y equals 0, which is just the x-axis, no? So this is the horizontal asymptote, y equals 0, right? So just put these double arrows in both directions, so then it's easy to plot. So on both sides of the asymptotes, put the double arrows like that for the vertical ones and the horizontal ones. Then we just need to connect them, right? So asymptotes are done. Then let me mark the inflection point and the turning point. So let me first mark turning point, minus 1 comma 1, minus 1 comma 1. Let me mark it like here. Let me take this as 1. So it's a maximum, no? So let me put a little peak here. So minus, at minus 1 comma 1 you have a turning point, a local maximum. So that is done. Then inflection point is minus half comma 8 over 9. So minus half, so somewhere here, this is 8 over 9. So there's an inflection point here. So mark that also, inflection point. Right, turning point done, inflection point done, asymptotes done. Now you have to draw it using the increasing and concavity, using that. So now we can do, first section is less than minus 2. First section is this side, less than minus 2 side. This section we have to draw in this section. Okay, so let's do that. So less than minus 2, concavity is what? Concaving down. Less than minus 2, function is also decreasing. Decreasing and concaving down. Decreasing and concaving down. Can I do this? No, that is increasing and that is concaving up. So decreasing and concaving down means what? I have to connect these two arrows. So there's our first section. First section has this shape. Concaving down and decreasing, right? So that section is done. Next section is going to be from minus 2 to your local maximum point, minus 2 to minus 1. So minus 2 to minus 1, what happens? It is increasing. Minus 2 to minus 1, it is increasing and concaving down. So then can I do this? No. I can't connect that arrow to the local maximum. That is not increasing, no, that is decreasing. So I have to do what? This down arrow has to be connected to the local maximum like that. It is concaving down, no, it is concaving down until minus half. This point, the inflection point. So then, right, so now we have to select which arrow to connect, down arrow or the up arrow out of these two. Now you have what? From minus half onwards. So after minus half, it is concaving up, and what is happening? It is decreasing, no? After minus half, it is decreasing. So concaving up and decreasing. So then this shape, concaving up shape, and you have to connect to that arrow because it's asymptote at y equals 0, no? So you can't cross this, no? So there's the full graph. So you have your turning point. There's the turning point, minus 1 comma 1, and there's the inflection point, which is minus half comma 8 over 9, right? So right, so that is the graph, right? Asymptotes are marked, x equals -2 and y equals 0, right? Okay, so that's the graph. Then what are they asking? State the smallest value of k for which fx is 1 to 1 on this interval, k greater than. So you have to find what a value of k, so that it is anything above that, it's going to be 1 to 1. State the smallest value of k for which fx is 1 to 1. So let's see, fx is 1 to 1. So 1 to 1 means what? 1 to 1 means we can use what? Horizontal line test, no? Yes. So draw some horizontal lines and see. This is not 1 to 1, no? There's two intersection points. So two intersection points. For which k value is this? Right. From where? Here we want to find what? Smallest value of k. So where you will only have one intersection point for horizontal lines. For anything above that. Okay, so this is the point now. Look at this point. The inflection point. If k is greater than -half, what happens? That represent this section, no? This section of the graph. That is 1 to 1. No? Any horizontal line only intersects that section only once, right? We can't. Can we go beyond that? Oh no. We can go up to the turning point, no? We can go up to the turning point, no? Yeah, up to turning point we can go, no? Not -half. K greater than -1, no? Up to there we can go, no? We will only have if we restrict it to this section. If we look at only this section from -1 onwards, all the horizontal lines will intersect once, no? Yes, so then the smallest k value is -1. K equals -1. Then in this section, function is 1 to 1, no? -1 to positive infinity, you have a 1 to 1 function. Yes. Can k be less than -1? No. Then you will have two intersection points for horizontal lines. For example, if you are here, you have two intersection points. So the smallest k is -1, right? So that is the part A of the differentiation question. Next we'll do part B, which is going to be the optimization question. Right, now let's look at part B. So shaded region shown in the figure is of area 45 square meters. It is obtained by removing rectangle of length x meters and width y meters from a rectangle of length 3x meters and 2y meters. Show that the perimeter L of the shaded region is given by that. Okay, so let's note down an expression for the perimeter L. So we have 2y, then this is 3x, 2y plus 3x, then there's another 2y here, there's another 2y there, then there's x, then another x, no, that's not x, that's y, no, sorry, that is y, this is y, this is y, so x plus y, then another x here, then this one is y, and finally this x. So what do we have then? We have 2y plus 2y plus 2y, 6y plus 6x, right? Yes. So perimeter is 6y plus 6x, right? We have to replace y. So to do that, we have to use this. Area of the figure is given. Let's write down a formula for area. Area is what? 3x into 2y, which is the big rectangle. Big rectangle area is 3x into 2y. From that, we have to remove what? This small rectangle, x into y. That we have to remove, that is x into y. So this gives us 5xy. So 5xy is equal to what? 45. That is given to us. Now area is 45. So then xy is equal to 9, and we have to replace y now. So y is equal to 9 over x. So that is equation 2. So sub 2 into 1. So what do you get? L equals 6 times 9 over x plus 6x. So L equals what? 6x plus 54 over x. And x has to be positive now because these are lengths. Right. So that part is done. That is simple. Find the value of x such that L is a minimum. So differentiate dl over dx. 6 minus 54 over x squared, right? So max or minimum occurs at stationary point. So find the stationary point or the turning point. dl over dx equals 0. So this gives me 6 minus 54 over x squared equal to 0. So that means 54 over x squared equals 6. Oh, x squared equals 9. So x equals plus or minus 3, but we know x is positive. No? X equals 3. Right. So then we just, what are they asking? Find the value of x such that L is a minimum. So x equals 3 is the value such that the perimeter is minimum. So we'll just show that this is a minimum by using the dl over dx sign. 0, 3. So between 0 and 3, what is the derivative sign? Substitute any value less than 3, and between 0, 1. You get what? Minus. And after 3, I can put like 4, and I would get what 60 54 over 16, this is positive, no? So what's this shape? Decreasing, increasing. This is a minimum, no? So at x equals 3 we have, so we'll write it as what? Perimeter is a minimum at x equals 3. Right. So you have to show that you at x equals 3 it's a minimum. So now then, yeah, that is done. Find the value of x such that L is a minimum. So perimeter is a minimum at x equals 3. Okay, you can also show that the perimeter is a minimum using the second derivative test also. Then you have to find what? D squared del over dx squared, which will give you what? Minus 54 x squared x minus 2, you get 108 over x cube, right? So this is the second method to show the x equals 3 is a minimum. So we found the second derivative now. Now substitute the turning point value, x equals 3, 108 over 27, which is 4. Second derivative is positive at the turning point, so that means what? X equals 3 is a minimum. You have a minimum at x equals 3. If the second derivative is positive at the turning point, it's a minimum. No, if the second derivative is negative, it's a maximum, right? So either you can use the first derivative sign chart or find the second derivative and substitute x equals 3 and show that you get a positive value. Then from the second derivative test you can say x equals 3 is a minimum also, right? So that's the 14th question, right? So next we'll look at the 15th question, which is what? Integration.